11Q Part 1. We're going to talk about 12.6 directional derivative and gradient. So last time we covered partial derivatives and we covered the chain rule. And when I talked about partial derivatives, I mentioned that partial derivatives are derivatives in the direction of the x-axis and direction of the y-axis. So what happens if we want derivative in any other direction? Because when you have any kind of a general shape, there we go, general shape, and you look at any kind of surface, this surface will have different slopes, different changes if you look in different directions. Now, if you take partial derivatives, you are necessarily getting the x and the y directions at that point. But what happens if you want to go at 45 degrees? What happens if you want to go at any other way? So that is what we are going to do with the directional derivative. We can find, remember with derivatives measure the change. They measure the change in function. And if we have the freedom to do that measure in any direction, well, we should, because that will tell us the change in any possible way. Now, remember what we have the partial derivatives, and partial derivatives will tell us the change in respect to x-axis, in respect to y-axis. And we also know that the unit vectors would carry the direction without changing magnitudes. So if you combine these two concepts, that the unit vector is going to provide direction and the partial derivatives are going to provide magnitude, and you put them together, you can get the derivative in any direction, technically. Because the direction will depend on the direction of the unit vector, which is what you provide, and then the function will provide the value of derivatives at the point at that vector. So let's take a look at I'm going to write the theorem. Again, all of the derivative stuff is still the same. We're not changing any of the derivative definitions. The limit definition is still the same in terms of limit h goes to 0 of f of x plus h minus f of x over h. So all of that stays the same. What we are learning new right now is that the theorem on the directional derivative. So let f be differentiable at point A, B, and let vector u with components u1 and u2 be a unit vector so I can actually put a hat on it because it's a unit vector in xy plane the directional derivative of f at AB is given as a simple dot product between the two partial derivatives and the unit vector. So directional derivative of f at AB in the direction of u is, we denote this as the directional derivative in u of f at AB as, and we have the partial derivative computed at AB, partial f at AB dotted with u1, u2. So it quantifies the change. Quantifies the change. Dot product. There is. Well, dot product is multiplication, except the dot product is multiplication for 2 dimensions, 3 dimensions, 4 dimensions. Multiplication is the dot product, one-dimensional dot product. So I want to call it a special case. It's just the first case of dot product. Dot product is a broader concept. Multiplication is part of it. All right, let's pick example from so here is your example. Let's go with example 8. Your function f of x, y is given as 2x squared plus y squared. And then let's go with the point A, B, 1, 2. And vector u, why? Vector u is given as square root of 2 over 2, square root of 2 over 2. Good luck. You got this. The art of plugging into the formula. But I would really like you to understand that partial derivatives are those, partial derivatives give you magnitude. Unit vector is length 1, so it doesn't impact magnitude, it just gives you direction. Put them together and you have the derivative in any direction. That's what it is. Now the dot product will give you a scalar, which means it is going to give you the numerical value quantification at the end. Yeah, like number 7. So the answer is always a number. I get 7 in this case is wrong. Yes. Well, you first find the partial derivatives, and this is the partial derivative in respect to x computed at AB. So AB is 1 and 2. So when you find the partial derivative is going to be in terms of x and y, right? Which means you're plugging in, this is your A and your B, so you'll be plugging those for x and y. No, you take the partial derivatives, because if you plug this stuff in and then take partial derivatives, it's 0. Right? So they will just be numbers. You take the derivatives first, then you plug in A and B and compute that, you will get a vector, and then dot that with roots, and you will get a number at the end. Yeah, partial derivative of x is done separately from partial derivative of y. Yeah, well, in this particular case, but yeah, because the book is one. You say do it. Yeah, you see the partial derivative. Find the partial derivative in respect to x. What's the partial derivative? Yeah. No splitting. You have a function. What's the partial derivative in respect to x? Compute that at 1, 2, since only x is in the right, compute it is 4. Separate line. Compute the partial derivative in respect to y. To y. Compute that at 2, you get 4. So the first vector is 4, 4. Dot 4, 4 with root 2 over 2, root 2 over 2, and you have. Yeah. I didn't trust you to write in. All right, so now let's decode the formula and see how this works. So when you are looking at the formula, we have fx computed at AB. So if you have fx, you have to compute the derivative, partial derivative fx. So that's going to be, when you look at it, partial derivative fx in respect to xy. We don't have to write it, but it is in respect to xy. Is going to be 4x. And the derivative of y squared is 0 because it's in respect to x. And then we compute fx at 1, 2. Now observe that you only have x, so you will only use 1. So that's 4 times 1 is 4. Then we compute fy. Partial derivative in respect to y, so 2x squared dies because there are no y's there. It's all constants. And then y squared is 2y. We compute the partial derivative at the point 1, 2. Since it only contains y, we use number 2, so that's also 4. So 2 times 2 is 4. So now we created, so these two together create our vector 4, 4, which is the first vector there. Directional derivative in direction of u of f computed at 1, 2 is going to be the dot product of 4, 4 with root 2 over 2, root 2 over 2. And when you multiply this, you will get 2 root 2 plus 2 root 2, which is 4 root 2. So 4 root 2. Scared me up there. So the formula here computes the directional derivative at a specific point on the surface of the object. You find the point, and then you figure out in which direction you want to look at, which is going to be the unit vector there. You compute both partial derivatives separately, and then you compute them at the point. Now, sometimes the partial derivatives, you remember the last class, will end up having x's and y's in their answers, and sometimes will not. So in this case, they didn't. So we get to use only one point at a time, but we'll have examples where we can find partial derivatives, and then your textbook has only 2 examples for this, and they're both very basic. So we can ask our friend Larson to provide more if you. By the way, you can get this book for 10 bucks, 15 bucks. This is the 7th edition. I learned calculus from this book. And it's the best, I believe, and my students, everyone who bought this book said it was the best read for calculus. And I also like, who is the student here who has the Rogowski book? Yeah. Oh, you have it too? You just want me to like you less now because you lied. All right. $884. Let's find another example of this so that we can. See, Larson has 12 problems and your book has 2. So here's the wonderful example from our friend Larson that involves e to the x and then sine and then, now let's not go that crazy, but one more example so you can practice this. So Larson's 7th edition, page 893, problem number 8. And the previous problem was number 8. Let's compare them. So Larson says, your function of xy is e to the negative x squared plus y squared. And straight. The point is 0, 0. And your vector u is I plus j. Oh, by the way, he likes to put these vectors with i's and j's rather than vector notation. There you go. Grind through the same formula, get both partial derivatives independently, compute them at 0, 0, and then do the product. Do the dot product from the vector you obtained with the vector you.
You can change it because it's not here. Click on the little arrow and you have the sizes. The stroke is the it breaks the entire line. It's a Microsoft stuff. It's simple. Yeah, oh my God. You saw the remember the Shining when he's hacking the axe into the bathroom? Have you seen that image for Windows 10? Awesome. I complained to I spoke to the Microsoft support. So they do Windows for the power line. Give a little bit of ignorance to them. They said they are trying to fix it, they update the firmware. So let's see. I'm going to try to turn it off tonight. I may put the button and see. Steve has the same problem. With any of the three surfaces that have it will work perfectly. And vibe in the same one because this is so I have no time. Do that once for everybody. Oh yeah.
You had plenty of time to figure out all the chain rules and things. Apparently, people are getting zeros here. I don't know. We'll see how it goes. So the partial derivative in respect to x, well, it's e, so copy the same and then chain the derivative in the numerator, in the exponent, sorry, and wow, that does give us 0 for this vector. Yeah, it is. Details. It's gonna pay attention. Thank you. It is going to work out. So fx at 0, 0 is going to be equal to 0. Fy is going to be symmetric, except my 2y over here. And we have fy at 0, 0 also 0. So now for our directional derivative of the function at 0, 0, we're going to have a vector 0, 0 dotted with a vector 1, 1, which is 0. All right, cool. It is what it is. So we know how to deal with this. Now, the next concept is the gradient vector. So the gradient vector. Gradient vector is a simply vector of partial derivatives, and it could be 2D, or could be 3D, could be any D, because as many variables as you have, you just keep taking the partial derivatives in respect to those variables. So gradient for 2D case is going to be, now the notation is the upside down triangle. We read this del. So del f of x y is equal to fx xy and then fy xy, and those two are functions. They could be functions. And then we have 3D case, so xyz is going to have three of these. So f in respect to x, xyz, and then f y, xyz, and finally z. There's just a notation for the gradient. So, you know, addition has the plus as a notation for it. So this is the notation for it. It's just upside down triangle. That's what we, and that is a vector. So you actually put the arrow above it. And you will see this symbol a lot in you know, physics. You will see this symbol a lot in advanced engineering and so on, because this is a very important concept. It's featured in Maxwell's equations, so it's a very important symbol.
40.
5, 6, whatever. It doesn't matter, because you just keep adding. Yes, just keep adding at the end. Whatever variables. Guys, you already computed gradient. So if you go to the previous example, all you need to do is to put this comma that. That's it. Because the gradient of the function is partial of x comma partial of y, which means this mess comma that mess. That's the gradient. Now we actually computed that before we actually put it together in a vector. But now we have a cute formula for for the directional derivative, right? Now the directional derivative of f of xy, let's say, can be written as the gradient of f dotted with u. It's a much shorter, it means the same thing as the previous one, and then you compute this at AB. You compute everything at AB. So, depending on which form you want to remember, you can remember the form. You can remember the vector form, which is the pink one, or the exploded form, which is the one on top. Okay, what else? So computing gradients. I think our book has quite a few exercises on that, which is good. Oh, look at that. 17 through 26 is computing directional derivatives with gradient. All right. We'll do that as well. So let's first do an example of just computing the gradient. 16 age of xy is given as ln of 1 plus x squared plus 2y squared, and compute that at the point P 2, negative 3. So what is the gradient of h? What is the gradient of h computed at 2, negative 3? Jedan, 5. Let's say it's good, huh? Good enough.
terms of how the people look like, how they behave, and all that stuff. So just to share understanding of who exists is winning the lottery that you can't even imagine. Imagine how many grains of sand you have in the desert, right? That's how many combinations you could have, possible individuals you could have, that you'll never split, ever. And you won the lottery to exist. So no matter what's happening, keep moving. You won the lottery to release that one. You gotta have that out of the lottery. Yeah, you can sit there and have to read books. Actually, the presentation is good. That's what you want. I'll bring the topic. The way the light and things work, that is just part of it. You decide to see the meaning for so that you understand. You don't You're so far into that. Yeah, that's why it's called share. That is all the reward. Yeah, that's why I don't want to. Yeah, we don't. That's why I don't go with you. No, I would ever refuse service here. And,
The solution is already on the board. I hope you all have the same answer. The first line here is just the gradient, and the second answer is the gradient computed at point 2, -3, which is where you just plug in x's and y's, 2 and -3, where they belong, and you compute the values. This is going to play a crucial role in the rest of the chapter, so you absolutely must know how to find the gradient and how to compute it as well. It's extremely important to be able to do that. It's the vector of partial derivatives. That's all it is. Defined as the vector of partial derivatives. And now, what do we do with this gradient? Why do we have it? What can we compute with gradient? Well, first of all, you see that the gradient is the part of your computation for the directional derivatives, right? It's that first factor in the dot product. But we also can find the rate of the maximum rate of decrease and the maximum rate of increase along the shape. So when you have something that is, let's say, wavy, that it's irregularly shaped, so it's not a plane, the rate of increase in different directions is not the same. Depends on from which way you look at it. So for any of these, the gradient will tell you the largest rate of increase and the largest rate of decrease. And that's one of the uses that you can explore and then later understand and then use eventually. So, directions of change. I don't need to be read. So if we have a function that is differentiable, obviously you have to have that in order to find partial derivatives, because gradient is vector of partial derivatives. So let f be differentiable at AB with del f different than 0 vector. Number one, f has its maximum rate of increase at AB in the direction of the gradient. Well, I'm just going to put del f. And the rate is the magnitude of the vector. The rate of change is just the magnitude of it. So you compute the magnitude of the vector because gradient is the vector. Number two, it has the maximum rate of decrease at the negative gradient, which means negative gradient looking the other way. F has its max rate of decrease at AB in the direction of negative del f at AB, and again the rate of changes the magnitude of the gradient. And the directional derivative is 0 at any other direction orthogonal to, right? So dot product there. So these are the three.
Isn't it negative magnitude for decrease?
Absolute value will kill it.
But it, oh, well, it looks like it's outside the magnitude of that. Would that matter?
It actually doesn't, because it's just a reference in which if you want to, if you look at the slope, right, positive slope, and then the negative slope, the rate of change is still, let's say you have a slope is 3 and slope is -3. The rate of change is still 3 over 1. The positive and negative sign is more of a convention to tell us which way it goes without using extra words. So I put the minus there to match the definition of the book, but it's the reference point. The physics, physics and engineering are very strict about it. Make sure that you have the reference point and then you have the next one. So yeah, but think of the slope of the line close to 3, -3, and the same connotation. So the rate of change is actually the same. I'm not looking at the book. Good. So let's take a look at the example of this. Actually, let me first show a graphic for this, so it might make some sense. Oh, I have to switch to the book first. So here you go. See you next week. What's the name for this shape? You must know it by now. Paraboloid. There you go. Paraboloid. So you have ellipsoid, paraboloid, hyperboloid, and you have the hyperbolic paraboloid, which is the self. And then you have those with the hyperboloids with 1 and 2 sheath, and then the cone and stuff. So this is paraboloid because no matter which way you cut, right, you remove this one, you remove that one, it's going to be parabolas. And then if you remove z, it is an ellipse. So it's elliptical paraboloid because it's not circle, right? If it's circle, you just say paraboloid. If it's ellipse, as this case, because x squared and y squared have different numbers in front, it is elliptical paraboloid. All right, cool. Now, you have elliptical paraboloid, and then you find the gradient for this function, and the gradient for this function, and then you center that gradient at a certain point, in this case, 2, -1/2. So 2, -1/2 gives you the intersection this way, it gives you the parabola that way, the positive, steepest ascent, and steepest descent. So those are the blue and the red arrows that show, and you can actually compute the value by simply figuring out the magnitude. So the problem is solved in a book, so you can read it because you know the letters, right? At the point 2, -1/2, you find the gradient at that point. It's 4, -3. You take the, so in a direction of 4, -3, which is in the xy plane, in that direction would be steepest to climb, and then in the direction of -4, +3 is steepest to go down. And then, which is good to figure out if you want to go rock climbing. And then 4 and 3, you take those magnitudes together, and that's actually the slope of the line over here. So that's 5. So that's the rate of change. The rate of change is 5. That means for every 1 unit, the 5 units up. So same interpretation as in your basic algebra course. The second picture over here shows the zero change, which would be along the curve this way because it's level, right? It's level. So if you cut it with the z-plane, z equals 3, z equals 5, z equals, there will be no change along if you walk on that circle because you're not going up, you're not going down. The change is measured as a dz in respect to x or dz in respect to y. Remember, because z is the function of x and y. X and y are independent variables. Z is dependent on x and y, and because z depends on x and y, we would look at the level curve. We didn't cover that yet. Wait. So you would look at this ring over here, which is the ellipse, and you would see that along that line, it's a zero change because you are always walking on the same floor. you are now at the third floor of this building, right? So no matter where you are in terms of while you're still on this floor, you are there is a zero change in terms of the height because again z-axis goes up. Now when you go to the second floor and so on, you will be showing that change as you're going down the stairs. So that's the thing. Now I wanted to find one of the examples so you guys can compute one of the here direction of steepest ascent and descent 27 through 32. So which one we're gonna do? Which one? 27 through 32. 27. F of xy is equal to x squared minus 4y squared minus 9. And the point is P1, negative 2.
Except you've got that before. Except
No. You just find the gradient.
And it's just the vector.
You will find the magnitude.
So
The positive vector, yeah, the positive vector is the direction of the ascent, and then the negative would be the descent, and then the magnitude of each will be how fast it's changing.
you never get any reference, I say. You're like, I was gonna say that you have to have the second one. What would you say like you all have like Star Wars series? No, so no, like the first three, all three ones. Even though people hate the new ones, like episode 1, 2, and 3.
The trick is that I have never read a single Star Wars book, but I read all the old and yeah. So, there is that thing that
That's why you were. So yeah, that was another. That was one of the times that I freaked out the most. I was reading the book. I was climb on it. He was trying to climb on the pole to escape from the crown monkey in the basement through the window. He was climbing. Reading. I think he's gonna make me. There's a feather going like this. And when I registered, there's something moving. I was home alone at the time. I was reading. It was something moving. Not alone. I jumped out of chair. Yeah. I actually have a picture like that. Would you say you like more than actual? No. Actually, I like there's a point that you know in about 2 hours period rather than. For instance, I'm not reading the show. They have I'm not reading because I started watching the show and I'm like, I haven't honestly, I haven't seen when I work. Yeah, I'm sick of it. You know what happened? My friend, he hyped it up so much. I think I saw the first episode and I was just like, what? Game of Thrones. He hyped it up so much and I saw it and I was just like, no problem. I don't like to read reviews that much. I just watch the next one. That's why I don't lose out on stuff. Yeah. Would you say like I do? Yeah. I watched 24. That was 24. Yeah. The whole plan is 24 stretched forever. So yeah, because I watched like 8 seasons of so I mean, it's really cool. And it's like, yeah, I made it the first 2 seasons, and they had as much stuff happening as 24 had the first 3 episodes. So I'm like, I can't just go slow pace. Watch. That's probably one of my all-time favorites. Scorsese. It's basically a movie about movies, but it's like primarily focused on like I want to see it. I want to make like a lot of things. It was a book first. That's what I was saying. Well, it's not great yet. People are leaving. Just like they're not related at all. For some reason, like, they are not.
We'll talk about it. Because they are. Normal means perpendicular, orthogonal, 90 degrees. All right, let's take a look at the solution of this problem.
Oh, yeah, we're still live. Hello.
Terrible class. All right, said that live. So the partial derivative in respect to x is 2x. Partial derivative in respect to y is negative 8y. And now we can create the del vector. The del vector is given as 2x negative 8y, and we claim that the steepest ascent is in the direction of the positive. So so this is the ascent, and then negative, which is negative 2x and 8y, is the steepest descent. And then we can figure out the magnitude. Oh, wait, we should first compute. Sorry. First compute this at 1, negative 2. So we're going to have 2 and negative 16. And negative is going to be negative 2, positive 16 for the descent. And now we want to know the rate of change. So we find the magnitude. Which is the magnitude of 2, negative 16, which is the square root of 4 plus, and then the square root, the square is 2.
How did you get negative 16 and then positive 16? Shouldn't it be the other way around?
I'll go back and check. Is equal to square 260. Someone has my back. How do I get?
Negative 2 is positive 16.
I have. So this is let's chase the green. So that's 2x, and x is equal to 1. 2 times 1 is 2. I'm happy there. Then I'm going to erase the green, and then I'm going to redo the green. Blessings. So we have the green, and then the negative 2. That's supposed to be positive there. Right here. It's a positive. And then when we do the negative, this one is negative. You were right. It does not change the outcome at the end. Good. Okay, so all of that stuff for 3 dimensions is the same. The last concept that we have to talk about, and then we're going for a break, is the gradient and the level curves, which is going to involve our tangents, right? So we have the theorem, which says given a function differentiable at a, b, the line tangent to the level curve of f at AB is orthogonal to the gradient del f at AB, provided del f AB is not zero vector. So if you have the level curve, and you remember how you get the level curves, who can tell me how we get level curves? Easy? Oh yes, set z equal to a value, okay. So we have some kind of level curve. There's the level curve. And then you pick a point, and here's your tangent. So that's your point AB on the level curve. This one is the gradient. That's all it is to it. Perpendicular, 90 degrees. That means the dot product between the two is 0. You can test that, check that. Variance in 3 dimensions. We already wrote the formula for it. Just add one more component. That's it for this one. And then when we come back, we will talk about tangent planes, linear approximations, and differentials.